In step 3, we prepared our physical model. We will now use the Analytical Model Generator AMG by SOFiSTiK to generate the analytical model. AMG streamlines the process of integrating structural analysis into the building information modeling workflow by generating and updating analytical models based on the physical model's geometry and user-defined configuration. Step 3 already played an important role, asking the user to carefully consider what elements and levels were to be defined for generation. This resulted in a clean and optimal model view assigned for generation. In step 4, there are further points to be considered, checks to be carried out, and a possible iterative generation approach depending on model complexity. However, you have full control based on the decisions you make. AMG is not a magic bullet. It is, however, a powerful, time-saving, model generation and coordination tool seamlessly integrated into the analysis and design workflow. To open AMG, we navigate to the Analyze ribbon. On the opened ribbon, we'll move the AMG tool panel off the ribbon and place in our workspace. Next, we open the AMG tool dialog box, and with no change made to the default configuration, we'll quickly progress through the Prepare, Generate and Coordination check steps to generate the initial model. Once complete, open the main system view to observe in isolation the generated analytical model. We can now visually inspect the model and carry out a separate analytical check. To carry out the analytical check, open the SOFiSTiK Analysis ribbon, select the Check tool. Our model contains 2 warnings relating to unsupported columns. As we've not yet assigned any supports, this is expected. Visually inspecting our model, we can also observe a couple of overlapping slab elements at level 0 due to steps in the slab. These will be manually addressed. We can also observe most columns terminate on the level 0 slab. Whilst this reflects the physical arrangement of pile caps situated directly beneath the slab, it doesn't provide an optimal analytical solution of discrete column supports to establish load path and load magnitude to foundations. This will also be resolved manually. Further inspection reveals the generation optimization has aligned the slab edge and columns around the external perimeter. This may or may not be optimal, for example when it comes to punching design further downstream in the analysis and design workflow, we will likely prefer a more realistic slab edge to column arrangement. The alignment of the wall and slab interface, service risers, main and half landings are already optimal. AMG optimization really working well, so we don't want to make changes here. We need to carefully consider the configurator options and balance automation and some necessary manual changes. Configurator prioritization is under your control to achieve the optimal outcome. We also have a number of columns with an aspect ratio greater than 4:1 which should be treated as walls in accordance with EN standard. We'll address this with changes to the AMG configuration. We'll now delete this model, explore and apply changes to the AMG configuration options and rerun the generation. Returning to the configurator, we can review our settings and adjust for individual preferences. As we are generally happy with the default configuration and acknowledging we have a few minor modifications to make, we recall we want to address the blade columns where the aspect ratio was greater than 4:1. Here we'll amend the settings, asking AMG to substitute the 1D elements for 2D planar elements. We can give our modified configuration a new name. Again, we quickly generate a new analytical model based on the new settings. Recall the only changes made were to the substitution of the blade columns. We can see AMG has generated the remaining structure as the first iteration but has now substituted the 1D columns with 2D planar walls of same dimensions in length and thickness. Turning our attention to the perimeter columns and slab relationship, we have some manual work to do here. This was an accepted compromise to keep the optimal generation for the more complex area of the core structure and its numerous interfaces. Navigating to the 2D analytical working plans, we'll address the slab edges first as these are very easy to address. We'll start at level 0. We select the item we wish to make changes to, and use the Edit Boundary function. A quick tip. I suggest you always use the Edit Boundary tool for making changes to planar elements and generally do this on a 2D plan view for slabs or 2D elevation or section for walls. This easy method allows you to snap to the background link model, and this method will generally overcome issues resulting from unintentional moving of any interconnected elements. There are a couple of penetrations which also require adjustment which we can address with the same boundary element tool. There is a further penetration at level 0 to address. You can see an edge is coincident with the axis of the 1D column element nodal intersection. Amending this may cause unwanted behavior. Let's try to amend and see. As suspected, the amendment affected the position of the intersecting column end node. I'll demonstrate two possible solutions to overcome this issue. Before we do, we'll undo the previous instruction. Both solutions involve deleting the penetration. The first solution is to copy a nearby penetration, place and amend its size. The second solution is to select the analytical slab and create a new opening with the Opening by Face tool. Any further openings not created where the configurator ignored holes less than the specified area can be reviewed, and you can manually create if required. Once we've addressed the slab edges at all levels, we progress to reviewing the column alignment. AMG has optimized the vertical eccentricity, so no manual changes are necessary here. Note, the eccentricity can be specified in the placement parameter in the SOFiSTiK properties panel. This means we get to simplify the analytical model whilst still accounting for known eccentricities that exist. Because we have some interconnected beams at level 1 with the perimeter columns, we'll temporarily disconnect these at the columns we intend to move. We can do this safely with the coordinate grab handles. To move the columns, we will open the 3D analytical view, specifically filtering only columns. This allows us to select the full stack of columns whilst in a top-down view, and we can select all columns in the stack and use the Move command to adjust their position. Once the adjustments are made, we can return to the 2D Level 1 plan and use the grab handles to rejoin the beam ends. Where a beam no longer aligns with the column, we can place an analytical rigid link to provide support to the beam end. Note, whilst the beams in this project are considered structural and modelled, they are not in this case structurally significant. The engineer should establish the structural importance, placement, interface with other elements and support conditions, and make their own modelling decisions accordingly that influence the analysis and subsequent design decisions. Looking closer at the columns on grid OQ3, establishing the dimensional offset being 75 mm, we can further refine the column alignment with the slab edge. Within the top-down view of the 3D analytical view, we select all the columns and beams along this grid line, and use the Move command to move exactly 75 mm by typing in the value in the direction of the move. After undertaking these changes, we take the opportunity to repeat the analytical check as we did earlier. We have similar warnings, this time the substituted column, now a planar element, shows as unsupported. Now we're satisfied with the model, we can address the substructure and supports. First, we'll neaten up our workspace. We can close AMG for the time being, and we'll take the opportunity to close inactive views, leaving us with just the working 3D analytical view. We want to address the substructure first. Recalling the original physical model, there is a mixture of different foundation levels, with some columns and walls extending below level 0 to a foundation level, whilst other foundations interface directly at level 0. We already decided to simplify the levels for the analytical model back in step 3, but this leaves us with some manual amendments and creation of new elements to address the gap between level 0 and foundation level before we continue to model the actual foundation supports. We'll start with the columns and then move on to the walls. As we already have analytical columns present in the model at level 0, it makes sense to utilize these. Extending the existing elements would be analytically incorrect for a number of reasons. Instead, we can copy, place, and adjust, and still benefit from the elements maintaining their section and material properties. Once we have our selected elements and have copied them with the copy tool, we open level -1 foundation and select Paste with the instruction Aligned to current view. Back in the 3D view, we can see they are aligned to foundation level, but retain their original length. We can now adjust their length with the grab handles. This is an easy process with the automatic snapping to level 0 as the element length is shortened. On completion of the columns, we can undertake the same exercise with the walls. Remember to use the Edit Boundary tool for this, setting the view to be on elevation. Again, the snapping function to levels makes this an easy task. A final observation from copying the walls was that we can see clearly the presence of a door opening in the substructure wall copied from the wall above. As this view is filtered to show walls only, we can temporarily change the visibility of the view filter to show analytical openings from within the view template. We can then delete the opening. After doing so, make sure to change the visibility state back to its original state in the Filters section of the View template. We now have our substructure complete and are ready to address the foundations. At this stage, as an analytical check and early confirmation our model is behaving as expected, before we spend time generating accurate foundation supports, we can rapidly apply supports temporarily to our model, generate the finite element model and calculate the self-weight load case. First open AMG again. Next open the main system. To rapidly apply supports to both columns and walls, analytical nodes need to be visible in the view. Open the View template and change the visibility setting of analytical nodes under the Analytical Model Categories tab. On the AMG tool panel, we can now select the Boundary Conditions tool and then Boundary Conditions for points under the submenu. Select all analytical nodes at foundation level, click Finish to complete the selection process, then assign the preferred boundary condition within the Properties panel. We undertake the same procedure for the walls by selecting the boundary conditions for Lines tool from the same submenu as before. Select all lines at foundation level, and choose your preferred support. We have now applied temporary supports to our model and are now able to generate the finite element model and calculate the self-weight load case. Before doing so, we can optionally carry out the analytical check and this time include a check for kinematic stability. In the SOFiSTiK Structural Properties panel, tick the Analyze Load Cases parameter, apply, then proceed to the Calculate command. Observe any warnings. These warnings can be ignored as they relate to load actions without assigned loads. Next, open the structural desktop with the SSD shortcut button, and once open you can select Load Case 1 and observe the behavior of the model. The supports generated here would be sufficient at an earlier design stage to inform the foundation solution. In this example, we continue with the replication exercise. Satisfied with the behavior, we can close SSD and progress to accurate modeling of the foundations. Benefiting from our predefined view templates and filtered element views, and with the help of Dynamo scripts, we can generate our foundations with ease and accuracy. We can observe in our analytical view of the foundations our link model and the previously defined analytical supports assigned to the base of our columns and walls. We can inspect elements in the link model by selecting the link model and using the Tab key to sub-select elements of the link model. Toggle the Select Links button in the lower left tool panel to enable the selecting of a link model and its elements. Upon selecting the link model, hovering and using the Tab key we can select the pile cap and observe its properties, notably its height. We can do the same with the pile. Our existing analytical supports are no longer necessary and will be replaced, so we'll delete these. As we copied the physical model, we can also inspect using the physical and analytical views in our working directory. Here we observe the piles, again inspect their properties including the pile number assignment by mark. We'll later automatically assign the pile reference to our analytical supports in readiness for calculation of forces to the piles, followed by the generation of an analytical pile schedule in Module 6, which includes updating the forces parameter values to the piles. You will observe in Module 6 just how quickly and easy the update operation is to provide pile forces data output in this BIM workflow. With the help of these views, we'll now address the foundations. To address the foundations, we have two components to consider: 1. The pile caps, and 2. The supports representing the piles. Open the SOF Level -1 analytical plan. First, let's address a 3-pile, PC3 reference pile cap of 1.2 meter height. Navigate to the Analyze tab and select the Analytical Panel tool, followed by Panel by Boundary from the sub-menu. From the Draw Tools panel in the ribbon, select an appropriate tool. We'll select by line. By tracing over and snapping to the endpoints, we create our panel. Note the local x-axis will observe a positive direction of the first line drawn, which we can change after the panel is complete. We can select the Align x-axis and then select an alternative line to reorientate the axis. In addition to the local Z direction, the axis directions are important for slabs and walls, but as we'll not be conducting any design of pile caps directly inside SOFiSTiK, this is not important as we only require the pile caps to act as analytical elements to distribute forces from the columns into the piles. We'll assign parameters to the analytical panel, first starting with its role, in this instance as a panel. Next, its thickness, followed by an analysis property. This property is not directly used by SOFiSTiK but is used in the element filters and view templates. We also assign various identity data parameter values in line with the company BIM standard being applied along with member grouping. This completes the pile cap exercise. We can repeat for other pile caps, or instead copy and place, and modify for each cap including the core cap in the space of a few minutes. To continue the replication exercise, we'll now address the piles. We'll use the copied physical pile elements to our benefit to generate the analytical counterpart. Autodesk doesn't allow the creation and placement of individual analytical nodes, so we instead use generated elements to provide the end nodes that we can then subsequently apply analytical boundary support to. After, we'll automatically apply the pile reference to our subsequent boundary support conditions. Let us begin. First, we'll use a Dynamo script to generate the analytical pile for each physical pile. To do this, navigate to the Manage tab and then select and click on the Dynamo player from the ribbon to open. The folder location may or may not be already pointing to the SOFiSTiK samples folder. If not, refer to the course instructions and manually point to this folder, which is the same location you were asked to place the Dynamo script before commencing this module. Scroll down to script number 903-1 and select the script name to open the script. Here you can see the default inputs already assigned for this project, which the script will use to generate the analytical piles. Click on the Run button to execute the script. You can immediately observe the results in the view. Back in the analytical 3D view, we can again see the generated elements, and when selected, we can see the reference added to the SOFiSTiK name parameter. As the generated elements observe the same physical start and end extents of the physical element, we have to bridge the gap between the base of the caps and core base to align with the analytical counterpart. Autodesk don't provide the same extensive alignment options for analytical objects as they do for physical objects, so instead we will manually align these. First, we'll make some global changes to the new elements to ensure they behave correctly in our model. As these elements only exist to allow placement and same naming of the boundary supports we'll be adding next, we select and filter the analytical piles. And in the Properties panel we'll change the element structural role to none, the same for section type. And again for the view filters and view templates, change the Analyze As to Foundation. We can see the elements now have the correct filter color and appear in other views. Next, let's bridge the gaps, using the coordinate handle and extending the top of the pile to the analytical foundation level. On completion, in our Analytical Foundation view, we will select, filter and use the temporary View Override Filter button in the lower left of our workspace to isolate our analytical pile elements and nodes. Next, using the AMG tool to apply boundary supports, we rapidly add supports, select the support type and apply to all the elements in one instruction. We can then reset the temporary view override, returning the view to its original view state. Next, we'll now copy the pile references from the analytical pile elements over to the boundary supports. To do this, navigate to the SOFiSTiK Analysis tab and click on the Set Names tool on the Utilities section of the ribbon, select all the elements in the view, and in the dialog panel, deselect all but support conditions. Select Edit Naming Rule, and delete the existing rule. We'll create a new rule using only the hostname string. Click OK and apply. The boundary supports now observe the naming rule of the pile reference. This completes the pile generation and naming exercise. For the balconies, two common types are encountered in a typical concrete frame. These are thermally isolated balconies with either 1. A continuous support via something like a rebar continuity system, or 2. Discrete support points with cast-in embedments into the slab. Balconies on this project represent the latter, i.e., discrete cast-in embedment type. We'll model a single support point representing this system, and in step 5, when we apply the loading to the model, we'll add loads to this single support before we then duplicate or generate a group for the purpose of further duplication. Here we select a suitable representative support member, and place whilst in a 2D structural plan view. We then apply the short form name to the SOFiSTiK filtering ID and assign the member grouping. We'll not be designing the support in SOFiSTiK, so we only need to consider a simple support condition to apply both vertical gravity and moment forces. These will then be accounted for in a load takedown of the building and also considered in the slab design further downstream in the analysis and design workflow. This completes the balcony modeling. Design elements play a crucial role in allowing the integration of finite element area results for single or multiple elements into line results. Open the main system view. Navigate to the SOFiSTiK Analysis tab and click on the Design Elements tool in the ribbon. We'll use these design elements as we progress through the modules. The first of these to be introduced is the tower element. Commonly used for seismic projects, we will use the tower elements to control the whole or parts of a structure for the assessment and application of wind loads and for the load takedown workflow. This part model represents a very simple system, but the original project has increased complexity and contains split levels and multiple structure parts. We'll visit this project shortly. In the meantime, we'll introduce a tower element to this part model. Here you can see a selection of design elements offered for use. We will select the tower element. The view changes to a top-down view and first asks the user to provide a name, define the top level, base level and intermediate levels that the tower is to consider. We can then arbitrarily place the tower and use the grab handles to adjust the plan size where the extents are moved just beyond the extremity of the foundations to capture the foundation's self-weight in the load takedown calculation. In the SOFiSTiK Properties panel, we can check the levels associated with the tower are correct and edit these if required. The levels were reviewed and defined already in Step 3, so we shouldn't need to make changes here. Tower elements and story levels work together to provide the results we require on a level-by-level basis. We briefly revisit the original whole building model to illustrate the use of tower elements in this model to address the parts of the structure and split levels. Here we can observe 3 towers. The first, Tower 1, addresses the structure from foundation level up to level 8. At level 9 we have split levels, these being level 9 and level 9 roof. Tower 2 addresses the structure from level 8 to level 15 roof overrun. Tower 3 addresses the lower roof structure at the level assigned as level 9 roof, and incorporates the core overrun to block Q. Looking at the Level 9 analytical 3D view with its assigned scope box, we can clearly see the structural arrangement at Level 9. As the slabs are stepped with no continuity between them, but both share same supports to their perimeter edges, the analytical arrangement observes the same. When we inspect the subsystem views, we can clearly see that level 9 belonging to Tower 2 is analyzed in isolation of the adjacent roof, and the same is true for level 9 roof belonging to Tower 3. Finally, if we look at the load takedown proforma dialog, this provides a very clear diagrammatic representation of the load takedown path for the whole structure. It also clearly shows how the split levels and different parts of the structure are treated for an analytically accurate load takedown assessment. This will be covered in Module 5. Whilst there are further tasks to address, this concludes the generation of the analytical model in Step 4. I invite you to review the learning in Module 2, open and inspect the completed part and whole models already provided, and continue your familiarization by completing the element number grouping assignment and addition of the short form naming applied to the SOFiSTiK filtering ID. Options for the splitting of walls into piers and spandrels will be discussed in Module 4 on the topic of lateral stability analysis. Next, we'll cover the application of loading in Step 5.